Should an engine fail in flight, its propeller control unit would sense a drop in RPM, and, in an attempt to maintain the pilot's selected RPM level, would move to the underspeed or fine pitch position. Centrifugal moments acting on the blade would cause it to rotate towards fine pitch. This would result in the propeller being put into a windmilling situation, with its pitch change piston abutting the fine pitch stop. The immediate result of this would be a very large asymmetric drag, which would yaw the aircraft violently towards the failed engine. A second possibility, if the propeller continued to windmill and drive the engine, could be a complete mechanical breakdown of the engine, and even an engine fire. So, to minimize drag, and also to prevent further possible damage to the engine and the aircraft, some propellers, particularly on multi-engined aircraft, are provided with a means of turning the blades edge-on to the air flowing over them. In this edge-on position, where no aerodynamic force is generated either forwards or backwards, the propeller will cease to rotate. This action is called feathering the propeller. If the engine had actually failed, there would be no requirement to unfeather its propeller. However, propeller manufacturers usually provide an unfeathering facility, by means of which, if appropriate, an engine restart may be attempted. This may be a requirement following asymmetric flight practice. The operating principle of the propeller control unit incorporated in a feathering propeller is similar to that previously discussed, in that the unit contains an oil pump to boost oil pressure delivered from the engine or reduction gearbox, and a hydromechanical governor for RPM control. There is, however, the addition of a feathering mechanism, the operation of which will be discussed progressively throughout the lesson. Control units with feathering mechanisms may be found on both turboprop or reciprocating aero engines. Dependent on the manufacturer and type of propeller system, the controller may be known as a propeller governor, a constant speed unit, CSU, or a propeller control unit, PCU. For the remainder of this lesson, we'll refer to the unit as the propeller control unit, or PCU. The controls available to the pilot are, again, dependent on type. Most spark ignition piston engines, and many turboprop engines, are equipped with a twin-lever cockpit arrangement, whereby the pilot has separate engine power and propeller control levers. In this arrangement, propeller feathering can be manually achieved by moving the propeller control lever to the feather position, or on some aircraft, by means of a separate feather lever. Some turboprop engines utilize a single lever arrangement, whereby the pilot is provided with a power lever only. In this arrangement, propeller pitch, RPM, and engine fuel flow, power, are simultaneously adjusted. Feathering may be achieved by moving the engine high-pressure fuel cock to the feather position. New generation reciprocating engines equipped with Full Authority Digital Engine Control, or FADEC, also use a single lever arrangement, whereby the pilot selects the required power setting and the propeller pitch angle is controlled either electronically by an electronic engine control unit or by a hydromechanical control unit. This diagram illustrates that the propeller control unit may contain a number of components which are additional to the basic constant speed system that we discussed earlier. The feathering mechanism provides a means of manually lifting the landed valve to the overspeed or coarse pitch condition when the appropriate control is moved to the feather position. The actions required to feather a propeller are dependent on the type of engine and propeller combination and the type of aircraft they are installed in. For single-acting propellers, this normally involves moving the propeller condition lever, or RPM lever, to the feather position. Moving the appropriate lever to the feather position mechanically lifts the landed valve against the speeder spring to its highest position, thereby simulating an exaggerated overspeed condition. The landed valve will remain in this position until the feathering control is moved back to its normal position. any oil in the pitch change cylinder can now drain away, allowing the spring or gas pressure, assisted by counterweights, to move the piston onto the feathering stop. To unfeather the propeller, the speed of spring tension is released by moving the propeller control lever to a position comparable to that of the serviceable engine, which of course is running at normal operating RPM. This moves the landed valve down and connects the reserve oil pressure line to the fine pitch side of the propeller pitch change cylinder. A reserve of oil pressure may be supplied by means of an accumulator, which is charged continuously during normal operation. By activating a release valve, oil pressure from the accumulator is directed to move the pitch change piston to fine pitch. Alternatively, some systems may utilize an electrically operated unfeathering pump, or, on some smaller systems, the engine may require motoring over on the starter to build up sufficient oil pressure. Once the propeller blades have moved away from the feathered position, the propeller will start to windmill, and as long as the engine has fuel and ignition, it should start. When an engine, which is fitted with a single acting propeller, is shut down after flight, the propeller should be at the fully fine pitch position. There is a considerable quantity of oil trapped under pressure on the fine pitch side of the piston in the pitch change cylinder, which is holding the propeller in the fully fine position. This oil pressure is being opposed by the force of the feathering spring. After engine shutdown, the trapped pressure will gradually leak away past the landed valve in the constant speed unit. As this trapped hydraulic pressure leaks away, the feathering spring is able to slowly push the propeller blades towards the fully feathered position. While this condition would be acceptable to a turboprop with a free power turbine, it would result in an unacceptably high loading on the starter motor of a piston engine or direct coupled turboprop. So, to prevent the feathering spring pushing the blades all the way to the feathered position, on those engines where a feathered propeller would cause stress on startup, centrifugal latch pins are incorporated in the pitch change mechanism. The latch pins are held disengaged by centrifugal force while the engine is running. As the engine RPM reduces, small springs behind the latch pins overcome centrifugal force, and they are allowed into contact with the piston mechanism. Typically, the value of the RPM at which the latch pins become engaged is around 650 to 700. After engine shutdown, the latch pins engage with a groove in the piston mechanism, which locks the piston. This prevents it from being pushed beyond a predetermined blade angle, and further into the feathered position by the feathering spring. When the engine is started and RPM increases, centrifugal force will disengage the latch pins. Fine pitch oil will quickly build up and hold the propeller against the fine pitch stop. Note that if a propeller engine combination does have a centrifugal latch mechanism fitted, it may become impossible to feather the propeller of that engine once its RPM has fallen below the latch setting value. This is because once they are engaged, the latch pins can prevent the piston being moved any further by the feathering spring. It is thus extremely important to complete the feathering drill before the RPM decays below this figure. Double-acting propellers do not have springs or gas pressure to assist in changing propeller pitch. Thus, all of the actuation, both to fine and coarse pitch, must be hydraulic. Engine or reduction gearbox oil is once again used as the hydraulic medium for this purpose. The inset diagram of a dry sump oil tank, which you may remember was used previously in the lesson on engine lubrication, illustrates how a protected source of feathering oil is provided. The oil pressure required for feathering the propeller is generated by an electrically driven pump, which may be activated by a feathering button in the cockpit. With the exception of operating the feathering pump, the basic control selection for feathering the propeller remains the same. That is, selection of the propeller control or condition lever, operation of a separate feathering lever, or on some turboprop systems, moving the HP fuel cock to the feather position. For the purposes of this lesson, we'll consider that we are feathering a propeller which has twin lever control. The propeller control lever is brought back through the fully course position to the feather position. Alternatively, where fitted, the propeller feathering lever is operated. This action lifts the landed valve in the propeller control unit upwards, thereby connecting the feathering pump oil line to the coarse pitch side of the pitch change piston, and allowing oil to drain from the fine pitch side of the pitch change piston. The feathering button in the cockpit is pushed in, energizing the feathering pump solenoid relay to supply the feathering pump. It also energizes the holding coil, which keeps the feathering button depressed for the time being. Feathering oil now passes through the ports of the landed valve, pushing the pitch change piston so that it moves into contact with the feathering stop. Oil pressure will now build up within the system, eventually operating a pressure-operated cutout switch, which will interrupt the supply to the feathering button hold-in coil. This causes the feathering button to release, which terminates the supply to the feathering pump solenoid relay, which in turn breaks the supply to the feathering pump.